These are the notes for section 2.5 part 3. These are the last notes for section 2.5. And I'm recording them during parent-teacher conferences. So if I have to pause, I'll just let you guys know and I'll pause really quick. So these notes are on two things called interpolation and extrapolation. So these are basically both forms of estimating. The first one, oh, and you should have a handout to take these notes on. I should have given it to you today. The first one is interpolation, and that's a type of estimating where we're estimating the coordinates of an unknown point that lies between 2 points. So the way you can remember that interpolation, it's kind of within our data set. We have data on either side of that point, so we're estimating something in between those two parts of data. That's interpolation. It's within the data. So the other kind of estimating we do is called extrapolation. It looks like extrapolation. People will say it all different ways too. So this is, again, estimating the coordinates of an unknown point that extends beyond the known points. So you can remember extrapolation, extend beyond. So it's not within the data that we have, it's outside of it. Maybe we have data up until 2016 and we're going to try and estimate for 2020. Something like that. That's extrapolation. So we're going to do a couple of problems that will require us to either extrapolate or interpolate or both. All right, so our first example here says, according to the National Assessment of Educational Progress, which is NEP, the percentage of fourth graders who are proficient in math has grown from 24% in 2000 to 39% in 2007 and 40% in 2011. We're going to estimate the percentage of fourth graders who showed proficiency, or I guess is that worded right, who showed proficient, who maybe were proficient in 2004, and then predict the percentage who will demonstrate proficiency in 2015. So the first thing I think I should do here is maybe write down all these data points I have. So I know that in the year 2000, 24% of fourth graders were proficient. In 2007, 39% were proficient. And in 2011, 40% were proficient. I listed my years as the X value because they are independent. The number of students proficient depends on what year it is. So I'm listing the years independent, which is X, and the proficiency percentage as their dependent Y variable. So even when these problems, I know in the book it doesn't say to graph it in this example, but you have to graph it. Yay. So let's graph this, and then we're going to use the graph to estimate those things that they asked us about. So I'm going to scroll down a little bit here, and let's see. I want to get up to, they asked us about proficiency in 2015, and it starts in the year 2000. Let me see if I have enough lines here to go up to 2015. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so 2015 goes one line off the graph, so I'm going to head and go with it. I'm going to use, for my years down here, I'm going to use that each line on this graph is 1 year, but I'm only going to mark every 2 years. So this first is 2000. This is 2002. Oh, I messed that one up. That should be 04. 06. 08. 2010. 2012. 2014, and then I'll put a little mark here. I know I'm going to use that for 2015 later. So I've got my years on there, and then we're going to put the percent of fourth graders who are proficient on my y-axis. So let's see. The highest percentage they gave me was 40%, so maybe I'll try to get up to 50% or so. Let's see, maybe if I go by 5, so let's try this out here. This would be 10%, 20, 30, 40. That worked pretty well. I have some extra room, but that's all right. So let's go ahead and plot those points that they gave us. We know that in the year 2000, 24% of students are proficient. So in 2000, we've got 24% of students proficient. In 2007, 39% are proficient. So we're almost up to 40. I'll go right below the 40 there. And then in 2011, oh, we just make it up to 40%. So at 2011, we just hit that 40% mark. So what you're going to do in this case is there's not a lot of data here. We can't really draw, it's hard to draw a line of best fit if you remember that from last year. So we're just going to draw some lines connecting these points together. There's not a whole bunch of, like if you had a big huge scatter plot, you could probably draw a line of best fit, but there's not really a great line of best fit here. So we're just going to use a ruler, get a ruler right now, go get up and get a ruler if you don't have one. We're going to just extend the line to connect those points. All right, so the first question they asked us, if I go up here, is estimate the percentage of fourth graders who showed proficiency in 2004. So if you look for 2004, it's right there. That's within our data. We have a data point both lower than that on the x-axis and higher than that. So when we're estimating in 2004, I just want you to note that right now what we're doing is interpolation, because this is within the data that we already have. So what we're going to do here is just go to 2004 on our x-axis, and then we'll go straight up until we hit that line that we drew. And then we'll go straight horizontally until we hit the y-axis to find about what that amount would be. So it looks to me like it's at maybe about 32%. So I'm going to say in 2004, about 32%. That's interpolation. It's within the data we have. Now, the second question asked us about estimating the percentage who will be proficient in 2015. Now, we have kind of an older math book, so at the time, 2015 was the future, but we're going to pretend it's the future now. So we don't have data up to 2015. Remember, our last data point was right here at 2011. So to estimate for 2015, what we want to do is pick your ruler back up, and we're going to extend that line and try to keep the same slope and go past out 2015, or out past 2015, so we can estimate what the scores would be there, or how many kids would be proficient. Now we're going to do the same thing. We're going to find 2015. We're going to go straight up. Oh, excuse me. And then we're going to go straight over as well as we can. And I'd say that, I mean, it's really not far above 40%, 41 or 42% maybe. So we're going to estimate now in 2015. And I just want to make a note to you that this is now extrapolation, because we didn't have any data out to 2015. Our data ended in 2011. So this is extrapolation. It extends beyond the data that we had. I'm going to say about 41% of those fourth graders will be proficient. So it jumped a lot in those first years, and now it's kind of leveling off. So we practiced both interpolation and extrapolation there. All right, let's go ahead and go to the second problem I gave you guys. So this one says gross revenue from Broadway shows for several years is shown in the table below. Use the data from 2005, 2006, and from the 2010 and 2011 season to find a linear function that fits the data. Then use the function to estimate the gross revenue from Broadway shows in 2012-2013 season. So I know this is kind of weird with the seasons. It's kind of like a school year or something, you know, or you know, a football season in the NFL. It starts in one year and it carries through the winter into the next year. So that's why these seasons each have 2 years in them. It's just one season, but it covers a part of 2 different calendar years. So what we're going to do here first is I want to go ahead and graph this just so we can kind of see what's going on here. So let's see, our revenue, okay, our season is definitely going to be the independent variable because the revenue depends on the season. Remember, time is almost always going to be independent variable. So let's put our season down here. And I'm going to use the letter T to represent this because I don't like to use S. So I'm going to use T for time. We can actually go ahead and just start with the 1999-2000 season right here at 0. Let's put 99. I'll put the year that the season starts with. And you don't even have to do that zigzag thing, because what we can do here, and you can do this whenever you're dealing with time, usually you're not dealing with anything at the beginning of time, like we don't have any data from then. So what we can do is say that T represents the number of years since the 1999-2000 season. So what we can even do to maybe make that a little more clear for you guys is in our table, this is going to be year 0. And then 2002, well, that's 3 years after that first season. So we'll call that really it's our T value of 3. And then this one is 6 years after. 2008 is 9 years after. And 2010 is 11 years after. So we're going to use these X values that are way smaller than 1,999 because we can just talk about the number of years since that first season. So we need to go up to at least 11 here, but they asked about 2012, so that's 13 years later. I think I'm just going to go by ones here. I'm just going to mark every 2, though, because I don't really have a lot of room. So this would be 2001, 2003, 05, 07, 09, 2011, 2004. Oh, messed that one up. One, 3, 5, 7, 9, 11, and 2013. And then let's see, our revenue. This one we can probably do the zigzag thing because we don't really need to start until 600, and then we need to make our way up to 1,080. So let's see, I'm going to do the zigzag thing. I'm going to start my revenue, which is in millions. I'm going to start it at 600 million. Let's see, 7, 8, 9, 10. I think I'm going to go by 50 million. So this will be 700 million, 800, 900, 1,000, and 1,100. 1,200 million. Whoa, that's a lot of money. So let's go ahead and if we put all these data points on there, it's going to be kind of like a scatter plot. And I want to go ahead and do that to show it to you guys. It doesn't do that in your book, but I want to show you. So let's put all those data points on there. In 1999, it was just a little bit above 600. In 2002, which is 3 years later, it was at 721. So maybe like right there. In 2005, it was at 862, so a little more than 850. In 2008, it was at 943. So in 2008, we go to 900, and then not quite up to 950. And in 2010, we're going up to 1080. So let's see, we are going to be at about right there, right? I feel like I did that one wrong. Yeah, I did do that wrong because it should be above 1050, which would be the midway point, so we're going to be about right there. All right, so if we look at our points, this is not a perfectly straight line. You could think about a line of best fit, which we talked about last year. Now, you guys, I don't want you to draw this line on there that I'm about to draw, but remember lines of best fit, first of all, it doesn't have to touch this point at 600. Doesn't have to. That might not really be a good data point for us. In this case, I'd say it kind of looks like it should hit there. Maybe it kind of goes like that. That looks like a good line of best fit. Now, in this problem, it's kind of funny. Usually problems don't do this, but they actually said use the data from 2005 and from 2010 to make this linear equation. So we actually don't want to make that line. We only want to go through the points from 2005 and 2010. I'm going to mark those in green. 2005 and 2010. We only want to use those points. So we're actually just going to draw a straight line, use a ruler that goes through those points. I'm going to have to redo mine a little bit, but I want to get our line as close as we can to just going through those two, because the problem actually told us to use those two. All right, so we've got our line there. Now, I know you're going to be mad at me because I'm not going to use the graph that much from now on, but I wanted to talk about a scatter plot and a line of best fit because we're going to use that a lot later. So now let's go ahead and try to find that equation. So we've got these 2 points that the problem told us to use. The 2005 data. So if we look at that, we're going to write this point as T, comma, and then let's say R. And R can represent our revenue in millions. So the 2 points they want us to work with are the 2005 point, which is this one, which is 6 years since the 1999 season, and it had an $862 million revenue. And then the other point is, I'm going to write it next to this one actually, is the 2010 season, this one, which is 11 years after the 1999 season, and they made $1,080 million. It's kind of a weird way to say that. So to write this equation, we're going to make a linear model, which it could be a graph. In this case, we're going to make an equation of this line. I'll be sure to be clear on a test or anything of what you need to make. So the first thing we need to do is to find the slope of this line. So remember, that's our change in y and change in x. So from 862 to 1080, that's our change in y. And that is, if you do 1080 minus 862, that is 218. So that's our change in y. Our change in x from 6 up to 11 is 5. So to write our slope, let me move this down a little bit here. To write our slope, it's going to be our change in y in the numerator, 218, and our change in x in the denominator, 5. Now, I know I always say leave your slope as an improper fraction, but when it's real life like this, it's okay to go ahead and divide it and just make it a decimal. If you divide those numbers, you get 218 divided by 5 is 43.6. Okay, so this means that their revenue increases by $43.6 million each year. Oh, that's a lot. They're making money. Maybe you guys should go work for Broadway. All right, so let's go ahead and try to work more with this equation. We know our slope, so we know our m. Now what we can do is we're going to try to write this in slope-intercept form. You can either put it in point-slope form, or you can just go ahead and start writing this in slope-intercept form. We know it's y equals mx plus b, so y equals 43.6x plus B. We want to know B. Okay, and I know that right now you might be looking at the graph and you're like, hello, it's 600 or 603, the one that was on the table. But we want to find the best y-intercept given those 2 points. Because the problem said use those 2 points. All right, maybe they think those years are really good predictors of what's going to be in the future and in the past. So we need to find out what B is. So what we're going to do is we're going to pick one of those points that we had before. I'm going to go ahead and use this one, 862. I'm going to use that as my x and my y. So instead of y, I'm going to write 862 equals, my slope is 43.6. I'm multiplying that by this x value that I have, which is 6. And then I write plus b. Now we just need to figure out what b is. So I went ahead and multiplied 43.6 times 6, and that is 261.6. So right now I have 862 equals 261.6, which is just those multiplied together, plus b. So now to isolate b, all I need to do is subtract this 261.6 from each side of this equal sign. And if you do that, we are left with b equals, I kind of just switched the side here, 862 minus 261.6, which is 600.4. It was pretty much 600, wasn't it? We maybe could have just used 600, but I want to make sure you guys know how to do that. Now, it told us to estimate it for the year, let's go way back up to this problem, the season 2012 to 2013. Now remember, if we put that on this table, 2012, that's going to be 13 years after 1999, and we're using our t as the number of years since 1999. So we need to plug in a 13 for t right now. So what I'm going to do is I'm going to come up here and I'm going to use my equation. I know my y-intercept, so I know my equation is y equals 43.6. Oh, you know what? I just realized I'm using the wrong letters. Instead of y, we should be using r, right? Our revenue is 43.6 times the number of years since 1999, t, plus our y-intercept, which we found out was 600.4. Now it wants to know the revenue for the year 2012, which is 13 years after 1999. So we're going to plug in a 13 for t. So my revenue is 43.6 times 13, I just plugged that in right there, plus 600.4. So remember, order of operations, we have to do our multiplication first. So we're going to multiply 43.6 times 13 and then add 600.4. So when you do that, you get $1,167.2 million. Okay, and think about whether that's interpolation or extrapolation. Were we looking for something within the data points we already had, or did it extend beyond it? If we look at our table here, it was extending beyond the data we had, so we were just using extrapolation to find that. All right, there's no problems to try on your own this time. Just make sure you come to class with those ready to use for an assignment, and you'll be good.